So one way to convert this to two-dimension is by using a dimensionality reduction method. We've seen principal component analysis, PCA, and we've seen SVD, or singular value decomposition. Now, singular value decomposition doesn't work really well with sparse matrices. So let's take a look at PCA and I would say a new way of dimensionality reduction called t-SNE. And the T stands for the student distribution. So it's T-distributed stochastic neighborhood embeddings. Yeah? Very complex word. I will try to explain what it means by way of an example. All right, so let us refresh our memories of what PCA was doing. Well, PCA, you have two features, and I want to bring this from two-dimensional to one-dimensional. What we're going to do in PCA is we're going to try to keep the variance as high as possible. Yeah? So, the variance on the x1 side is like this. On the x2 side is like this. Yeah? Quite big. So if I would draw a line here and project these points of this line, your variance is going to be smaller. So the real line to draw would be this one. Yeah? And you'll have some points here, and here you have another 3 points. Yeah? This is what PCA is doing. So you always go and look for keeping the variance as high as possible. So you have a distribution with a mean mu and a standard deviation sigma. What PCA will do is it's gonna center the data around 0, and it's gonna try to preserve the variance. So sigma should be roughly the same as sigma prime. Yeah? Now the problem with this methodology is that you lose local structure, because these 3 points here, they were actually a little cluster, whereas now they're just, points on a flat line. And that's where t-SNE comes in. t-SNE will aim at keeping local structure. So in this case, if we look at the problem from the viewpoint of x1, you have the distance of x1, x2, and x1, x3. Then we have x1, x5, and x1, x4. Now if we're going to do a t-SNE, basically what will happen is that we will keep these points and try to preserve the distance here, right? Try to preserve. And here this can also be seen as a local cluster. So the x4, x5, yeah, we will also try to preserve the distance, right? What we will not try to preserve are the two long red lines here. We don't commit to preserve these, but we commit to preserve the cluster. That's why 4 and 5 is on the left of this cluster, but here 4 and 5 is on the right of the cluster. Yeah, because we do not commit to keeping the distances here. So if you apply the t-SNE on such a matrix, you're basically going to have a vector space. And what you see here is that, man, woman, king, queen, our people are clustered together, and our fruits are clustered together. And there's more, because you see that the relation between king and man is similar than the relation between queen and woman. Even more, if you take the king vector, you subtract the man vector, and you add the woman vector, then you will see that you'll end up with queen, geometrically. Yeah? So this is quite fantastic. And basically what we want to do is we want to have such an embedding matrix, or word embeddings, yeah, that we can reuse. So there's two ways you can train. You can train this this feature, or you will reuse. Reuse, and this is then called transfer learning. Transfer learning, and this is exactly the same as we did for convolutional neural networks. Alright, so now that we know what the concept of word embeddings is, let's now take a look at word2vec and GLOF.